Welcome to the mathacademy.net channel. And welcome to our series on deconstruction in mathematics education. My name is Bo. Today we address the question, mathematics is hard, or is it? Last time we looked at primary school. Today we look at secondary school. And welcome to our guest, Alan, who uses deconstruction in his work.
Thank you, Bo.
Alan, can you please repeat what deconstruction means to you?
Well, Bo, to me, deconstruction means what it says, destruction and reconstruction. It is the method that is used by postmodern skeptical thinking that dates back to the ancient Greek sophists. The sophists warned against patronization that is hidden in choices that are presented as nature. So to avoid hidden patronization, false nature must be unmasked as choice. And to deconstruct then means to discover or to invent alternatives to choices that are presented as nature.
Thank you, Alan. And can you please repeat your short answer to today's question?
To me, the short answer to the question, mathematics is hard, or is it, is that mathematics is not hard by nature, but by choice. Mathematics is made difficult by its missing links.
And what do you mean by missing link?
I use the term missing link to indicate that mathematics has lost its link to its root, the natural fact, many. However, if this link is established again, then mathematics will once more become a science about many. And accepting it as a natural science will make mathematics easy and accessible to all, instead of difficult and accessible only to few.
Will you please repeat the 5 missing links in primary school?
I will be glad to. The first missing link is the total. We only write numbers, and always exclude the total. The second missing link is the missing transition from sticks to icons, showing that there are 5 sticks in the 5 icon, etc. The third missing link is not using cup writing to report the result of counting many by bundling, and placing the bundles in the unbundled in separate cups, thus separating them with a decimal point and including the bundle size as a unit. The fourth missing link is the missing use of recounting when changing units. And the fifth missing link is the missing emphasis on mathematics as a number predicting language.
Thank you, Alan. And that brings us to the remaining 3 missing links?
Yes, Bo. The sixth missing link is the difference between soft and hard operations. Let us write the total 456, as we say it, that is, as 4 hundreds, 5 tens, and 6 ones. We see that we count by bundling in tens, and that we total by uniting bundles of bundles, and unbundled. Thus the total is not a number, but a calculation that adds 3 stacks, a stack of 4 10 bundles, of 10 bundles, and a stack of 5 10 bundles, and a stack of 6 unbundled ones. However, the 3 stacks are not added on top of each other. They are added next to each other. So in what we can call hard algebraic addition, stacks are added on top of each other, while in what we can call soft geometric addition, stacks are added next to each other. And adding next to each other as geometrical stacks is in fact integration. Also we see that all numbers carry units, ones, tens, and tens, also called hundreds. Finally we see the 4 ways we unite numbers. We add, we multiply, we power, and we integrate.
I now see why we use the Arabic word for uniting, algebra. But Alan, can you please specify a little?
Certainly, Bo. If we want to add 1/4 and 2/3, we can do it in 2 different ways. We can add them on top, as hard algebraic addition. Then the units must be the same, so we recount the 2/3s to 1.24s. Thus the total is 2.24s. Or, we can add them next to each other, as 1.37s.
But Alan, 4 times 5 is still 20, isn't it?
Again, Bo, looking at the number 456 we see that 5 times 10 means 5 tens. Likewise, 4 times 5 just means 4 fives, which may be, but doesn't have to be, recounted in 6s as 3.26s, etc. or in tens as 2.010s. So soft geometric multiplication repeats adding on minus top, while hard algebraic multiplication re-minus counts in tens, making 2 times 3 sevens, not 6 sevens, but 4 tens and 2 ones, equals 4.2 tens, equals 42.
And what is the seventh missing link?
The seventh missing link is reversed calculation. Going forward we ask, 2 plus 3 gives what? Going backwards we ask, 2 plus what gives 5? Instead of trying out alternatives, we can predict the result by inventing an inverse operation to addition, called subtraction or minus. This allows the answer to be predicted by the calculation, 5 minus 2. So by definition 5 minus 2 is the number x that added to 2 gives 5.
But isn't 2 plus x equals 5 an equation?
Well, an equation is just another word for reversed calculation. And since the equation 2 plus x gives 5 is solved by the number x equal 5 minus 2, we see that solving an equation means isolating the unknown by moving numbers to the opposite side with the opposite sign.
Does this also apply to the other operations?
Indeed it does. Since 6 divided by 2 is defined as the number x that multiplied with 2 gives 6, we see that the equation 2 times x equals 6 again is solved by moving the number 2 to the opposite side with opposite sign, that is, by x equals 6 divided by 2. Likewise, the equation x to the power of 3 gives 8 is solved by moving the exponent 3 to the opposite side as the third root. And the equation 2 to which power will give 8 is solved by moving the base 2 to the opposite side as the 2-based logarithm. Finally, the last of the 4 basic operations, integration, is moved to the opposite side as its opposite operation, differentiation. Again we see that calculations predict numbers.
So what is the 8th missing link?
The last missing link is per numbers. Per numbers only occur as percentages, meaning per 100. However, recounting also gives meaning to per 5, to per 7, etc. So returning from sticks and strokes to the real world, all totals have physical units, meters, kilograms, hours, dollars, etc. As an example, we can look at coffee, where 5 kilograms might be recounted as $8. This means that the quantity-to-price relation can be described by the per number, $8 per 5 kilograms, or 8 per $5 per kilograms. To find the cost of 20 kilograms, we just 3 minus count 20 in 5s by saying T equals 20 kilograms equals 20 divided by 5 times 5 kilograms, which is the same as 20 divided by 5 times $8, which is $32.
So proportionality is basically about per numbers?
Precisely. And so is integration. Integration just means adding per numbers. To add 2 kilograms at $3 per kilograms, and 4 kilograms at $5 per kilograms, we can add the unit numbers to 6 kilograms. But we cannot directly add the per numbers. To add the per numbers, we transform them to unit numbers by multiplication. This gives the area under the per number graph. Thus the 6 kilograms cost 2 times $3 plus 4 times $5, which is $26. So the total per number is $26 per 6 kilograms. This shows that per numbers are added by their areas, that is, by integration, that is, by adding next to each other.
So Alan, you think reopening these 8 links will change mathematics from hard to easy?
Yes, Bo, I do. Mathematics becomes easy when presented as a natural science, grounded in the natural fact, many. To deal with many, we simply count and add. First we total many, by counting bundles and unbundled, using cup writing to report counting results as decimal numbers with units. Once counted, totals can be added on top or next to. If added on top, the units must be the same. So a total might have to be recounted to shift its unit. Thus recounting is the root of proportionality. And adding next to is the root of integration, also occurring when adding per numbers that come from recounting totals in different physical units. Finally, any calculation can be reversed, and the unknown number can be predicted by opposite operations. So to solve an equation, you simply move numbers to the opposite side, with opposite sign.
Alan, it seems so simple.
And Bo, it is simple. However, if you remove the 8 links to its root, the natural fact, many, mathematics is transformed from a natural science into what might be called Mandarin mathematics. That is why the mathacademy.net is created, so teachers can learn about and teach mathematics as a natural science about many.
What do you mean by Mandarin mathematics?
It is interesting to compare the Chinese and the Korean alphabet. The Korean was made to allow as many as possible to read and write, and the Chinese had the opposite goal. It was created by a Mandarin class possessing public jobs that they wanted their children to inherit. Consequently, the Mandarins invented an alphabet so difficult that only Mandarin children had the time and support to learn it before the exams. The French thinker Bourdieu says that Europe might have get rid of its autocratic kings, but their administrations still remain, and they are still manned by a Mandarin class that use mathematics as what he calls symbolic violence, to ensure that the Mandarin children will inherit the public offices.
But why is mathematics specially useful for this purpose?
The word language is learned when growing up, in contrast to the number language. So by removing the 8 links to its root, the natural fact, many, the Mandarins have succeeded in reserving mathematics for their children. Other means are forced classes with variable timetables to prevent daily lessons from providing a serious learning.
Do you know of any Mandarin class that deliberately tries to make mathematics difficult?
There doesn't have to be one, as demonstrated by the French thinker, Foucault. Foucault shows how once a certain way of talking about things, a discourse, has established itself as a discipline, it will discipline not only itself, but also its subject. Meaning that once Mandarin mathematics with its 8 missing links has been established as the dominating discourse, it is impossible to talk or teach outside this discourse, and to stay in office, Mandarins must follow orders given by the discourse, and in this way they reproduce the discourse. Also, the subject of mathematics, the total, is forced to silence both itself and its nature as a decimal number with a unit. Instead, the discourse declares that unnatural numbers without a unit and with a misplaced decimal point should be called natural. This creates huge learning problems. But it serves well the hidden agenda of the Mandarins in the public offices.
Thank you, Alan, for sharing with us your view on the question, mathematics is hard, or is it? In these 2 sessions we heard about the 8 missing links of Mandarin mathematics. Next time at the mathacademy.net channel we will look at deconstruction of fractions. Again we will ask, fractions is hard, or is it?